Hello, I'm Evan MacNeil from the University of Calgary, and I'm here to talk about this paper on non-hyperelliptic genus 3 curves that I've co-authored with my former master's thesis supervisors, Michael Jacobson and Renate Scheidler. Non-hyperelliptic genus 3 curves are also called C3-4 curves, so I'll be calling them by that name mostly instead. So we'll start by briefly highlighting what we did in this paper. So we produced fast explicit formulas that fully describe C3-4 curve divisor class group arithmetic. Now, formulas for this existed already for adding any two reduced divisors, thanks to Arita. And some faster formulas were developed specialized to the typical case due to Abu Salem and Corey McDeesey and other authors. The typical case is the case that arises almost always when working over sufficiently large base fields. We've managed to improve upon both sets of formulas in our paper. Why is this significant? Well, this is part of an ongoing project at the University of Calgary to fully describe divisor class group arithmetic on genus 3 curves. I have colleagues who worked on the hyperelliptic curves while I worked on the genus 3 non-hyperelliptic curves, C3-4 curves. This is useful in testing generalizations of elliptic curve conjectures to genus 3. This includes the Sato-Tate conjecture, the Birch and Swinnerton-Dyer conjecture, among others. Even more broadly, this is useful in computing L-series of genus 3 curves, which is a part of testing these curve conjectures. Previously, Arita developed an algorithm to add any two reduced divisors on a C3-4 curve and output the reduced divisor equivalent to their sum. He represented divisors by the reduced Gribner basis of a polynomial ideal and classified divisors into 20 different types according to the form of that reduced Gribner basis. His algorithm was very general, but it did assume that the base field was sufficiently large. Over very small base fields, he handles some things recursively in a way that might not terminate on those small fields. His work is also slow in comparison to the later developments. Flom et al. Developed a series of formulas that were specialized to the typical case, outputting the reduced divisor equivalent to the divisor sum, or an error value if the sum wasn't typical. Now, over very small base fields, that error value is going to show up very frequently, but Flom et al. Were interested in cryptographic applications where the base field was very large, and so that worked just fine for them. Corey McDeesey and Abu Salem improved upon that, and until now they had the state-of-the-art for typical case arithmetic. I'll note as well that they represented divisors by two ideal generators, but these generators didn't form a reduced Gribner basis like in Arita's representation. So we'll define a couple of the key objects that we're working with. A C3-4 curve is a non-singular algebraic plane curve over a field K that's defined by a polynomial of this form. Like elliptic curves, a C3-4 curve has a single projective point at infinity. And if the base field is of a characteristic other than 2 and 3, then this curve is isomorphic to one given by a shorter polynomial equation below. So here's an example of what such a curve might look like in the real plane. A divisor on a C3-4 curve is a formal sum of points that remains fixed under Galois automorphisms on K bar. That's the algebraic closure of K. In the divisor class group of C, every divisor is linearly equivalent to one of the following form. That's a sum of n finite points, not necessarily distinct, balanced out by negative n times the point at infinity. For simplicity's sake, we refer to n as the degree of the divisor. A divisor is reduced if n is minimal among all divisors in its class. And each class has a unique reduced representative divisor. It's an important fact that the divisor class group of a curve is isomorphic to the ideal class group of its coordinate ring. And what that means is that every divisor can be represented uniquely by a polynomial ideal. Different authors choose different representations for the ideals. We've chosen to follow in the footsteps of Harita and represent ideals by their unique reduced Scribner basis. Under this group isomorphism, the sum of two divisors is the same as the product of ideals. The least common multiple of divisors is the intersection of ideals. The greatest common divisor corresponds to the sum of ideals. And we have a fourth flip operation denoted by a bar that is related to the quotient ideal. The least common multiple and the greatest common divisor satisfy the identity A plus B equals LCM plus GCD. And the divisor can be reduced by flipping it twice, so the reduction of A is just double bar A. And this gives rise to a high-level algorithm for adding divisors. So given ideals ID and ID prime, representing the divisors D and D prime, to find an ideal that represents their sum, I just multiply the ideals and then compute two quotient ideals. So I can multiply ID by ID prime and compute a reduced Scribner basis for that product. Then I can compute these two quotient ideals and the reduced Scribner bases for these. And then the resulting ideal that I get after the second quotient is exactly the divisor that I'm looking for. Now in 2018, Corey-McDesy showed that the second and third steps can be combined into a single reduction step that's cheaper than even the second step alone. So that's enough for the background. We can talk now about what we actually did in this paper. So we generalized the work of Corey-McDesy in a couple of ways in this paper. First, we generalized his work to work for non-disjoint divisors as well. That is, we can now add divisors that share a point in common. So Corey-McDesy computed the sum of divisors by computing the kernel of the quotient of Riemann-Roch spaces, which are vector spaces. This works just fine when the two divisors are disjoint, having no points in common. But more generally, the kernel gives the least common multiple of the two divisors, which just so happens to coincide with their sum when the divisors are disjoint. We handled the non-disjoint case by also computing the greatest common divisor through the image of the quotient and then recursively using the identity D plus D prime equals LCM plus GCD. Now the GCD is always going to be a reduced divisor, but the LCM might need to be reduced before we add it, thus the double bar above it. And we show in our paper that this recursion terminates. We also generalized Corey-McDesy's work to handle atypical divisors as well, and we did this by allowing the size of the Riemann-Roch spaces to vary. Lower degree divisors can be handled by using smaller spaces, where atypical divisors require larger spaces relative to their degree. And putting this all together, we managed to derive explicit formulas describing all atypical cases that arise during divisor addition, including over finite fields of characteristic 2 and 3. We also got some improvements in the typical case. Now, the first way that we improved upon on this case is by identifying a couple of values that Corey-McDesy was computing that weren't actually needed later down the line. So we avoid computing those values, which saves a few multiplications. We also note that whereas Corey-McDesy's representation of divisors is by two polynomial generators of their ideal, our reduced Scribner basis representation requires a third polynomial, Now this requires a bit of pre-computation to find a third polynomial, but this ends up paying off in the end. We also save an expensive inversion operation at the cost of some multiplications by doing a variation on Montgomery's trick, and we'll argue soon that this inversion trade-off for multiplications is actually worthwhile. Now this addition framework doesn't work when the two divisors that we're adding are identical. If we're adding d plus d, well, the quotient map that we're trying to compute the kernel and image of is actually just the zero map, and we don't get much information out of that. So when doubling, we show in our paper how to find a suitable divisor A that's equivalent to D, then we add D plus A instead. Thanks to our reduced Scribner basis representation, A can be very quickly computed. And then we fall back on the addition algorithm where our savings there will apply as well. So this gives us an improvement when doubling divisors. And as before, we managed to describe with explicit formulas every atypical case that arises when doubling divisors. When it comes to reducing divisors, Corey-McDeasy already showed how to efficiently reduce a typical degree 6 divisor. That's the combination of those steps 2 and 3 earlier that we mentioned. We generalize that result to all divisors. So this table sums up how expensive it is to add and double divisors using different authors' formulas. So for example, in our paper, using our formulas, we're able to add 2 divisors in the typical case using 1 inversion, 111 multiplications, 3 squarings, and 99 additions in the finite field. I'll note that in Arita's paper, he counted squares as multiplications, and neither Arita, Flown, nor Corey-McDeasy counted additions in their papers. The addition counts for Corey-McDeasy's algorithms is provided by myself after implementing his formulas in code. So we can see by looking at this table that compared to Corey-McDeasy, the previous state of the art, we use 1 fewer inversion and many fewer additions at the cost of a few multiplications and squares. Now that savings of 1 inversion is very significant, and in order to convince you of that, we perform some benchmarking tests to see exactly how much time is saved when computing using our new formulas. So we implemented our formulas and Corey-McDeasy's formulas in Sage and ran benchmark tests to see how many divisors each set of formulas could compute in 10 minutes. So the benchmark test was as follows. We fix a prime number p, then we randomly choose a C34 curve over the finite field of order p. Then we randomly choose 2 divisors a and b on that curve. And then we compute the Fibonacci-like sequence where d1 equals a, d2 equals b, and every subsequent term is just the sum of the 2 before it. In order to test addition, that is. And to test doubling, we compute the sequence a, 2a, 4a, 8a, 16a, and so on. So we see how many divisors we can add using the addition benchmark sequence and how many divisors we can double using the doubling benchmark sequence in 10 minutes, and these are the result of those benchmarks. So we ran these tests several times over different prime numbers of different sizes with various curves over those primes. And we found that, for example, we ran these trials 23 times over prime numbers on the order of 2 to the 32. These are word-sized primes. And we were able to add a total of 126 million pairs of divisors using our formulas, whereas we were able to add 112 million pairs of divisors using Corey-McDeasy's addition formulas for an improvement of 12.74%. Using our formulas, we were able to compute 120 million doublings, whereas we were able to double 108 million doublings we were able to double 108 million divisors using Curry-McDC's formulas for an improvement of 11.37%. I found a more significant improvement over very large prime numbers. That's likely due to the increasing cost of inverting a number in a finite field over very large finite fields. And we found the most significant improvement over very small primes. And that's due to the fact that our formulas are able to handle all of the atypical cases explicitly, whereas Curry-McDC's formulas, his algorithm needs to fall back on slower, more generic arithmetic that isn't described in his own papers. We also see this discrepancy between 69% improvement to add over small primes, or 23% improvement to double over small primes. That large gap is probably due to the fact that atypical cases arise much more frequently in addition compared to doubling. So to sum up the contributions in our paper, we took ideas from Arita, Curry-McDC, Abu Sail, and put them together. By using Curry-McDC's algorithms and applying them to Arita's representation and a few other ideas thrown in there, we were able to generalize Curry-McDC's algorithms to work for atypical cases while also simultaneously getting an improvement in the typical case. We also relaxed assumptions on the curve equation in order to handle curves over fields of characteristic 2 and 3. And we were able to neatly handle non-disjoint cases with the LCM and GCD method from before. If you want to improve upon this further, it's still possible to eliminate an inversion in some of the atypical cases, although this is likely a lot of work for a very small gain. Something more promising is that my colleagues at the University of Calgary have been able to apply Schenk's new comp algorithm to genus 3 hyperelliptic curve arithmetic and have gotten some great results out of that. And so one wonders whether something similar can be applied to C3-4 curve arithmetic. So thank you for listening to this talk, and many more details and an implementation of the formulas can be found at the GitHub link displayed on this slide. Thank you.